All right. Good morning, guys.
Morning.
Oh, that was so sleepy. You're almost done. It's almost Friday. I mean, it is Friday. You're almost done. It's almost the weekend. We can start yesterday. All right. Does anyone have any questions, comments, concerns before we get started today? A little bit of housekeeping. What should you be working on right now? I mean, not right now. You should be working on class right now, but what's that? Yeah, homework number 5, right? The one that's due Wednesday. Because what is also due Wednesday? First exam,
So you
right?
have moved it. Something moved.
What's that?
So you have moved it. Maybe it was somewhere else.
I did. I moved it to Wednesday.
Okay.
What's that mean?
So, how does the take home gonna work? Like, you give it to us today and turn it in Friday, like no homework?
No, it's going to work exactly the same as the homework assignments. It's on Blackboard. It's an assignment on Blackboard. You go to it, you see PDF, do your solutions, scan them in.
Oh, but did you already give it to us today?
No, it'll drop Monday at 8 o'clock. So it'll drop Monday at 8 a.m. and it'll be due Wednesday
At midnight?
at midnight. Yeah.
Okay.
So, any other questions about that? Yeah.
On Monday.
Clear your calendar. It shouldn't take long. I said I don't expect it to take anyone more than 2 hours to get through. Sounds like a lot, but you got 3 days.
Do we have the same weight as self-study assignments? They have a little bit more weight.
What's that?
The take home
Has a lot more weight than the self-study assignments. Yeah. Yeah. The each self-study assignment's worth like 0.5% of your grade.
Really?
Yeah. Yeah, they're not worth anything. And
That is.
they're supposed to be for self-study. Then you take the exams, which are worth like 15% of your grade, and you do well in those. Right? That's the
That's
idea.
1%.
But isn't like the final, like the overall self-study?
Really?
What
That was
is
kinda
it?
like-
What's that?
Isn't like the actual like full grade of all the self-study like quite a lot?
Yes, the average of all of your self-study assignments is a big chunk of your grade.
So I guess it collects up to like what, 50 points?
Something like that, yeah. But the exam is worth a lot more on its own
Of course.
than any of the self-study assignments, yeah.
How many exams do they have?
I'm planning to have 4. I have a weird sneaking suspicion that they're only gonna be 3.
3, yeah. Yeah, just 3.
Right now, we're planning on having 4 exams. Based on how things are going, I bet we're only gonna have 3 exams.
Is it like we're behind schedule or like?
It's because we're behind schedule, yeah.
Is the final part of this week?
Yes, yeah, the final is not a separate thing.
Okay.
You will be given it during the final exam like window, but it won't count any more or less than it will not count any more than the other exams. It also won't be comprehensive, right? So it'll be just over those chapters that we covered since
It
the
would
exam
just be
before.
called final exam.
What's that?
It would just be called.
We call it the final exam just because it's the last exam. Yeah.
Which chapters will the take home exam be about?
Say it again.
Which units will the take
The
home-
ones that we've just done. So the exam that drops on Monday is units 1 through 5. So today we're gonna start unit 7. Yeah, man, moving on.
7?
What's that?
Unit 7?
Yes,
Are you skipping 6?
we are skipping 6.
No wonder I didn't see that, but whatever.
Yeah, Unit 6 covers this concept called the Quine-McCluskey method, which is a really arguably very cool way to like optimize Boolean expressions. It, however, is very time consuming to do by hand. And we've already spent a lot of time optimizing Boolean expressions. It's time to move on to other stuff. So we decided, even in the preface of that textbook, it says you can drop Unit 6 if you want to. So yeah, so we're going on to Unit 7. That's why the assignment is assignment number 7, right? Like, just keep them locked into whatever unit that we're working in. So yeah, so don't be confused by the fact that we just completely skipped the number 6 altogether.
You can make it like extra credits.
You don't want that. Like I said, it takes a long time. It's really cool. It's much more geared towards like writing like a computer program to do it for you.
Oh, it's not.
But it takes a long time to do it. So it's fast to implement it on a computer, and you can do like, 64 variable expressions in a computer, right? But even doing like a 4 variable by hand is pretty tough. So, all right, any other questions? All right, so we are into unit number 7. Today's lecture is all about what we're going to call multi-level gate circuits. If we have time, we're also going to briefly mention NAND-gates and NOR gates, although we'll talk about them in more detail on Monday. So multi-level gate circuits. So we spent the last couple weeks kind of getting standardized, kind of getting formalized about how we do our Boolean expressions. In this unit, we're going to kind of do the same thing, but for the actual circuit designs themselves. So we're going to take that sort of basic stuff, that's sum of products, the product of sums, and we're going to sort of apply it to actually drawing or designing the logic circuits, and we're going to tweak it just a little bit. So let's start things off with a definition. And that is, well, what do we mean by level of gates? So by the book, level of gates is the maximum number of gates. Cascaded in series or connected in series between a circuit's input and its output. So level of gates, the maximum number of gates cascaded in series between a circuit's input and its output. So let's draw one and talk about what that actually means. I wonder if these are kind of like the Among Us characters. Right. So, one thing to note, when we're talking about level, we're going to do a thing. All right, this is going to freak you out too. We will assume that all the variables and their inverses are available. Which is to say, the part of the circuit where we like invert it, we're not going to draw the inverters anymore. We're just going to say A and A prime as inputs to the circuit design. So when we draw inverters at the very beginning, we don't count those as part of the levels, is all that says. We'll start with A prime, and B prime as inputs to our circuit. So let's take a look at one. All right, so I got this guy that's got A and B. Feeds into an AND gate. Feeds into an OR gate with actually D and E. And then another AND gate. That's got F and G. And then feeds into an OR gate with input C. Together, they feed into another AND gate, which is cell, feeds into an OR gate with an input S, and we're going to call that output Z, which is a function of all those variables. So kind of a big, weird-looking, arbitrary logic circuit design. And so all we care about right now are just the levels. And what we do is you essentially start with the first gate you hit, you work your way back. I want to add another note to this. Now, levels must consist of the same type of gate. It's not a hard and fast rule, and we will break it from time to time, but for now, go with this. Levels must consist of the same type of gate. So you have a level of OR gates, and a level of AND gates, a level of OR gates, and a level of AND gates, and so on and so forth. So, conveniently, we've already organized this circuit that way. So we work backwards. The last gate in the circuit, before the output, is level 1. Then we have level 2. Then we have this group of OR gates, that's going to be level 3. And finally, we have this group of AND gates, that's going to be level 4. So it takes 4 levels to realize this circuit. And that's all there is to it. So when we design our logic circuits, we're going to start to organize them in these terms. And we'll see why later on. All right, any questions on the concept of levels? They got the same gate, the same types, level 1, level 2, level 3, level 4, all the way back until you reach the end. Now sometimes it is convenient, or actually most of the time, it's convenient to be able to sort of do an analysis and do a count of the levels, the number of gates, the number of gate inputs and stuff to get a sort of measure of the circuit without having to draw the logic diagram. So we're going to draw what's called a tree diagram for this circuit. I'll erase all this text now. All right. Tree diagrams. Okay, so let's use the same, we're going to use the same circuit as this, but we're going to write it as a Boolean expression. I'll leave out the variables because there's a ton of them. So Z is equal to A and B or C and D or E or FG, all that for H. So, is this expression in any of our standard forms? No, man, it's all soup, right? Which is why it's got such a messy logic diagram. Okay, so when we draw the tree diagram, all we're going to do is sort of group together the operations in kind of a branching structure. So you've got to sort of take a moment, take a look at it, figure out what are the operations that are going to happen first under the order of operations, and we'll combine them. So A and B, and F and G happen. And next to the dot, you'll mark how many inputs there were to that node. So there's 2 here.
Why do you have A, B, or C when those don't link the same gate? Because that's A, B, or D, or E.
Oh, because I wrote it backwards. In my notes, I got it backwards. So yeah. F, G, A, B. Good catch. Okay, thankfully that has nothing to do with this. So, next up we do the next level. Right? So that's going to be the stuff that's inside each of these sum terms. So we'll take the result of that first node and tie it in. We'll also tie in that C, and that's going to have 2 as well. Then we'll take this whole sum term, we'll tie in the result of that and the E, and the D for 3. Then the next step is we have to AND all these guys together. That's going to be 2. And then finally, all of that gets ORed with the H. And then also has 2. So, that's our basic structure. It's how we draw a tree diagram. Pretty simple, and it's a lot faster than drawing out the logic diagram. All right, so the important things that we derive from this diagram are first, the number of gates Here we have, you should just count the dots, 1, 2, 3, 4, 5, 6. Next up is the number of gate inputs. If you tally up all the numbers, 2, 4, 6, 8, 10, 13. And finally, the number of gate levels. And just like with the circuit diagram, here you're going to start at the bottom. Level 1, here's those guys. Level 2, level 3, and level 4. The number of gate levels is equal to 4. We will use the tree diagram and these three metrics to kind of quantify the efficiency, I guess you would say, the optimizedness of our designs. All right, questions about that?
Yeah.
What's that?
Does it matter which end you start on when counting the levels, or do you have to start
Yes,
at the end?
not for this, it doesn't matter, but for the way, for some applications that we're going to use to, when we use this,
Mhm.
it's going to matter.
Okay.
Yeah. So you want to know, there are things when we convert that we're going to convert it to other forms, and it involves changing things at like the odd levels and stuff like that, or the even levels. So that matters, yeah. So always start at the very end
Okay.
as level 1. All right. Any other questions about that? Okay. So next up, let's do this. There are a couple of standard forms, just like there are standard forms for Boolean expressions, there are standard forms for logic circuits. So, standard forms. All right. And two of these we've seen already, we just haven't called them what they are. So the first one, called an and/or circuit. I'll go and write out the definition. It's a two levels circuit consisting of level and gates followed by one OR gate at the output. So an and/or, a two-level circuit consisting of a level of AND gates followed by one OR gate at the output. It'll look something like this. So AND gate with some inputs that all feed into a single OR gate on the output. This one we've seen a lot, right? What standard form of a Boolean expression gets us the standard form of a logic diagram or a logic circuit?
Sum of products.
Yeah, sum of products. And we've got sum of products. We're going to get an and/or logic circuit. All right. Harry says that. Number 2 is going to be the other one. Or and. closed. The level of OR gates. Followed by one AND gate. At the output. So this is the one that is the level of OR gates, all feeding into a single AND gate on the output. The standard form of Boolean expressions gives us this. The other one, right? Product of sums. All right, I'm just going to bounce back and forth. All right, so those are the two ones that we've seen a lot before, right? Because those correspond to our standard forms for Boolean expressions. Next up, we got OR. So let me go 3. Or and or. This one's slightly different. So this one is a 3 level. Logic circuit. Composed of a level of OR gates. Followed by a level of AND gates. Followed by a 1 OR gate. At the output. All right, that's going to look something like this. OR gates with some inputs feed into some AND gates, maybe with some other inputs that all then funnel into an OR gate. So 3 levels, starting with OR gates, then AND gates, then wrapping up with 1 OR gate. Yes, sir.
I was just wondering, why you just leave one gate that has 2 inputs on you for all the others 3 inputs?
It's just a draw.
Oh.
Yeah, don't worry about it. It's just a sketch. All right. All right, let's see. The last one. It's kind of dumb. It's not really a standard form. We had and or and then or and or. You also have and or and, but we're not going to list it. And finally, what we'll call number 4 is a circuit of and or. This loosely translates to anything that's not one of the first 3. So a logic circuit consisting of NAND-gates and OR gates. In no particular order. So, anything that's not one of our standard forms. Oftentimes, we will start with a circuit of AND and OR and have to convert it to one of our standard forms. Much in the same way you had to start with a random Boolean expression and convert it through multiplication and through factoring to one of our standard forms. All right, I know that's kind of boring, but we got to listen to it. Good place to start. Any questions before we work an example? All right. So, I'm going to start here. Everyone has this written down. So what we're going to do here is sort of define a Boolean expression, or start with a Boolean expression, and then sort of see what it looks like to represent them in all of the different forms. So, this example, we can say explore different ways to realize the Boolean function f. It's a function of a, b, c, and d, and is equal to the sum of midterms 1, 5, 6, 10, 13, and 14. Now, before we do anything, what we have to do is take this and optimize it, right? You never want to just start with the raw Boolean expression. You want to optimize that first, and then mess with it to get the different forms. So we're going to do that with K-man. These are still hopefully kind of fresh in your minds.
You want a 4x4?
Yeah. So we got A and B on the top, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and then we list them all out. So we're going to have 0, 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, there's not a lot interesting that we can do with this one for the minterms, as we just have these groups of 3. Now, can we group these groups of 3 together? No, they're going to be powers of 2. So we kind of just have to block it out. So we'll say that f is a function of a, b, c, d. This first one is going to be what? A prime, b prime, or excuse me, a prime, c prime, d. Or to the next one, that would be b, c prime, d. Or then down here, we'll have b again, and then c, d prime. And finally, let's do down here, or this last group of 2 will give us A, CD prime. Alright. So that's our minimum sum of products. It's helpful to also go ahead and grab over here the minimum product of sums. And how do we get that?
The zeros.
Group the zeros, which conveniently do a little bit better. So they're going to go, let's see, to the top row, which is going to give us, so it's 0, 0, so that means we're going to have what?
C plus D.
Not C plus, but C or D. We'll do this row, which will get us C prime or D prime. Then all we have left are these 2 groups of 2. We'll do the top one. So 1, 0, 1. So it's going to be A prime, B, D prime. A prime or B or D prime. And then finally, this last group 2 is going to give us A or B or C prime. Here, B or C prime. All right, so those are our 2 minimum solutions. Any questions about this? Yeah.
Why can't we group like 3 variables together?
It's against the rules.
Binary.
Remember, they have to be, the groups have to be sizes that are powers of 2.
Okay.
Okay, 1, 2, 4, 8, 16. Right? They can't be bigger. All right, any other questions about that? Okay, so the first 2 realizations are pretty easy, right? Because they're the ones we already know. So let's start with the and or. And that's just the direct implementation for this guy, right? So that's 1, 2, 3, 4 AND gates. Let's see. 1, 2, 3, 4. And 1 or 2, right? They're all 3 inputs. A prime, C prime D, B, C prime, D, B, C, D prime, and A, C, D prime. Now all 3 can be organized in that case, so that's F. Should be pretty comfy realizing our stuff in this circuit form. One thing I want to do first, or before we move on to the next form, let's go ahead and write it out as our, let's do the tree diagram. A, C prime is A prime, C prime, D prime, or B, C, D prime, or B, C prime, D, or B, C, D prime, or A, C, D prime. And let's see. We got 3. Get 3. Get 3. Get 3. And finally, input of 4. So it's got a level 1 and a level 2. So our core metrics are, for this one, number of gates is how many? 5, good. Number of gate inputs is, say, 16, good, yeah, 3, 6, 9, 12, 16. And finally, the number of gate levels is equal to 2. All right. So there's the realization and the analysis of representing this Boolean function as an and or logic circuit. It's basically the case. Any questions about this? All right. Can I erase it? Because we're going to get to the next one. All right. So next up, let's do the or and. That's just going to be the direct realization of our product of sums. That's 1, 2, 3, 4. What was right here? Was it C prime? Good. 3, 4. All right. So 4 gate, 4 gate, 4 gate, 4 gate, 4 gate, 4 gate. Starts with C or D, then C prime, D prime, 3 inputs, A prime, B, D prime, and then 3 inputs, A, B, C prime, and they all feed the big lane. Yes.
It's not be dumb, but how do you know like if you use product of sums or some products for each like combination of gates?
What do you mean?
Or like for each of the standard forms for your and or and?
Yeah.
How do you know if you use the top one on the left or the bottom one? Some products or product of sums.
Like how you know which one goes with which one?
Yeah.
The top one, the sum of products will always go with the and or, and the product sums will always go with the or and.
Oh.
All right. So let's draw the tree diagram for this guy. And we'll have what? C of D, C prime or D prime, A prime or B, or D prime, A, B, A or B, or C prime. So we know it's going to be 2 levels. It's got 2. Next one's got 2. Next one's got 3. Next one's got 3. Final level has 4. And we had a level 1 and a level 2. All right, so we do the count, number of gates. 1, 2, 3, 4, 5. Number of gate inputs. Equals 14. And number of gate levels equals 2. So there we go. Any questions about that? Those two are pretty easy, pretty straight up. one more. All right. Or and or. The next one's a little bit trickier because it does require us to manipulate our minimum sum of products expression just a hair. So let's start with that. We've got x function of a, b, c, and d is equal to, we got a prime, c prime, d prime, or b, c prime, d, or b, c, d prime, or a, c, d prime. And if we want to get it, so it's in the form for and or. If we want to get it into or and or, we look for places to factor out. So in the first two terms, we can factor out c prime. That's going to give us c prime and a prime or b. Or in the second term, the last two terms, we can factor out the c, and that gives us c and I got missing steps somewhere. Oh wait. Steve. And then do on. Factor out the c prime and d in both of these terms. C prime d and a prime or b. See, sometimes I can catch myself too. And over here, the c prime and d, or c and d prime, and a or b. So now we can go ahead and draw our tree diagram. And it's going to start, because of order of operations, here with these ors. That's going to be 2, and 2. And then the and, c prime, d, the result of a prime or b, that's 3. Same deal over here. And then finally, they all get ORed together. And that's 2. All right, so we've got level 1, level 2, and level 3. And let's see, the number of gates. Is what? 1, 2, 3, 4, 5. Number of gate inputs is equal to 12. What's that? 12. 12. And the number of levels is equal to 3. So, we won't worry about drawing it for the sake of time. But here's a question. So the first one, the and or, had how many? Or like this. It had how many gates? It had 5 gates. It had 16 gate inputs and had 2 levels. Or and had 5 gates, 14 gate inputs, and 2 levels. And this guy, the or and or, has 5 gates, 3 levels, but only 12 number of gate inputs. At the end of the day, it's going to be the number of gate inputs. It's the most valuable thing. More levels is okay, but it gives you less. If it gives you less gate inputs. So this is where we kind of achieve our next level of optimization, right? We optimize the Boolean expression using our K-map, and then here we look and see which of the standard forms might actually give us a better result by being able to factor out a little bit. Even though we moved our Boolean expression into a non-standard form, we were able to achieve an actual logic circuit design that was a little bit more optimized. So that's the process, right? Start with your generalized expression, your truth table or whatever, optimize the Boolean expression, and then you're going to take a look at your standard forms of logic circuits to see which one of those is going to give you the best result. Cool. All right. So that is, I guess, it for today. Are there any questions, comments, concerns? All right. In that case, like I said, get that Unit 5 assessment done. It's a lot shorter than the other ones, so shouldn't take you as long. Just going to do some K-maps. Get that done so it's not getting in the way when you're trying to do assignment, or do exam 1. Michael on Discord asks, will assignment 5, guys, I'm not quite done yet. On Discord, they asked, will assignment 5 questions be on the exam? Yes, they absolutely will. So, all right, there's nothing else. Have a great weekend. Be safe. Enjoy the football game. Thank you. For the players. All right.